Oh, welcome everybody. Good afternoon. My name is Jeff Strager, and welcome to our webinar, Energy Dispersive X-ray Analysis, Practical Insights from Fundamentals to Real-World Applications. Just want to introduce to you before we get into the educational part of our session. I want to introduce a few slides on our company. We'll make that really brief and get right to the matter at hand. And then I will wait to the end of this and I'll introduce our guest speaker, Dr. Eric Lifshin, Professor Emeritus, UA Albany. Just a few notes on our company. We've been in business here for many, many years in electron microscopy and characterization techniques. Located in Bedminster, New Jersey. That's our building right there. We have a team of 6 people. Goes across from myself, who is the principal and founder, to Kyle Crosby, our PhD sales engineer, Lisa Strager, our manager of operations, Rod Hoy, service and application specialist for electron microscopy, to Lulu, our bookkeeper, to Jason, who runs our e-commerce and logistics department. We're a distributor of capital equipment, and we're a proud representative of Zeiss here in the Central Atlantic region, where we offer electron microscopes, 3D X-ray systems, and dual beam systems all the way down from New York City as far west as Pittsburgh, Pennsylvania, down south as far south as Virginia. And we've been a partner with Zeiss here for a number of years, and we're very proud of that representation, as well as everything else that we represent. But looking at some of the other solutions that we provide, we certainly are a distributor of some unique TEM solutions. We're the distributor in the United States for nanomegas, which is a 40 stem per session crystallography solution. We do represent a few unique TEM holders from Melbuild and Insight Chips. Melbuild specifically has a very unique holder that is specifically designed for battery research, double tilt, LN2, vacuum transfer. Insight Chip is a liquid TEM cell holder, which has a very unique membrane design, which allows you to do high resolution imaging in a liquid cell. We also represent quantum detectors, direct electron detectors for 40 stem. And on the analytical side, in addition to providing EDS on the electron microscopes and Raman at times, we have a standalone laser ablation, laser ionization, TOF mass spectrometer benchtop system, which uniquely characterizes lithium all the way to uranium. Very easy to use, desktop plug and play. And we also offer Raman spectrometers and microscopes. On the specimen prep side, we represent a Swiss company called SafeMatic for carbon and sputter coating systems. Unique thing about that product there for sure is its ease of use, but also as an automated carbon threading system, allows up to 60 carbon evaporations with no user interaction. We have an automated dehydration critical point dryer, and unique to any offering on the market with respect to sample cleaning, sample preparations, we have a multimodal UV light plasma and heat cleaner, which for some of you on the TEM side that are dealing with a lot of contamination, it's interesting to see how this will address an entire holder that's having issues with respect to analysis. And we have some plasma cleaning solutions. We do have a website with 2,500 SKUs. We offer precious metal sputter targets, Schottky emitters, calibration samples. We have one of the largest offerings of SEM sample holders, inert gas storage and vacuum transfer solutions, metallurgical supplies, light microscopy supplies. One thing I would mention too on the precious metal side is we do have a really nice reclaim program. So for any of you out there that have a lot of precious metals sitting in your drawer and you wanted to put it to good use, recycle it and get credit, please reach out to us and we can go from there. So without further ado, I would like to introduce our guest speaker. I'm going to stop sharing at this point and offer and give him the ability to share his screen. So while he's doing that, I will introduce Dr. Eric Lifshin. Dr. Eric Lifshin is a highly respected expert in electron microscopy and microanalysis with decades of experience in energy dispersive X-ray spectroscopy and related analytical techniques. Dr. Lifshin is a professor emeritus at UA Albany, part of SUNY, formerly the manager of the Materials Characterization Laboratory at GE Corporate R&D, and a past president of MAS. Awards include MAS Fellow, Peter Duncombe Award, Presidential Award, 2 IR 100 awards. He's held academic and research positions where he's contributed extensively to the advancement of microanalytical techniques and their practical applications. Dr. Lifshin is particularly recognized for his work in quantitative X-ray microanalysis, detector technology, and the interpretation of complex spectra. Over the course of his career, he's authored numerous scientific publications with more than 100 papers, 11 patents, and co-author, editor of 5 books, and has been an invited speaker at international conferences and technical workshop. He's known for his ability to translate complex scientific concepts into clear, practical guidance. He's trained generations of scientists. And for some of you that might remember, he's been a staple at the Lehigh Microscopy School for years. And he's been noted to be effective in his use of EDS and electron microscopy techniques. So without further ado, I'd like to hand it over to Eric. And Eric, thank you very much for joining us today. The floor is all yours, sir.
Okay, can you hear me? Let's start with that.
Yes, we can. Yes, sir.
Okay,
good.
By
the way, one more thing before you go, Eric, before you start. Listen, everybody that's participated today doesn't have a microphone, but there is a question and answer and a chat. Please feel free as this goes along, because we do want to answer questions if there are any. So please feel free to put your questions in that Q&A button at the top, or even the chat, and then we'll get to them as we get to the end of the webinar. Okay, thank you, Eric.
Yep. All right. Well, first of all, you can tell from Jeff's introduction that I'm no spring chicken, but I am happy to talk to all of you from beautiful East Sandwich, Massachusetts, out here on Cape Cod Bay. In fact, this talk is going to span a period of my involvement in microanalysis, which really started a long time ago, back in 1962. And during that period, I've had the opportunity to work with many of my heroes in the field, and they have been very helpful to me. I'm at somewhat of a disadvantage here in that I don't know all of you, and therefore I don't know your level of experience or interest. And so what I'll try to do is drive down the middle of the road and hope that some of you will pick up some interesting pointers if you're very experienced in the field, and others will get an initial exposure, which I hope will lead you to further studies. Let me remind you of a book that probably at least I had to read when I was in high school, called The Tale of Two Cities. And one of the cities was Paris, and the other was London. And this is a different tale of two cities, in that one is still Paris and the other is Cambridge, but that's not so far from London. And it's also a tale of two cultures, a culture of microanalysis, and that brings me to mention the very important name of Raymond Castaing, who was the developer of the electron microprobe, which was first commercially introduced in 1956, and also Professor Charles Oatley at the engineering department in Cambridge University. And he and his students, some of whom you probably know the names, Dennis McMullen, built the first SEM. He was followed by other people, include Oliver Wells and Tom Everhart. So all of you of SEMs are familiar with the Everhart Thornley detector. In the SEM, as it was developed, it was really a tool for trying to get higher spatial resolution and more three-dimensional imaging than was possible with optical microscopy. Say less than 20 nanometers compared to a couple hundred nanometers in an optical microscope. On the other side of things, there was an interest in trying to analyze things that were in the micron range, as compared to much larger samples that had to be done by wet chemistry. And if you look at the scientific literature at that time, optical microscopy, along with various mechanical and electrical tests, were the key to characterizing materials, as well as detailed analytical chemistry. And this work was conducted in government laboratories and university laboratories and industrial laboratories. And they tended to have distinct groups. So if you're in chemistry, you were kind of part of the chemical establishment. You'd probably wind up going to what was called the Pittsburgh Conference. If you were in the SEM world, you would maybe go to the ITRI conferences in Chicago that Johari hosted for many years. And if you're in the micropro world, you would go to the Microanalysis Society. And if you were a TMP person, TMs had been out for a while, you would go to EMSA, the Electron Microscopy Society Meeting of America. So these were the two cultures. And what was interesting and I want to talk about is how these came together to provide X-ray analysis to the scanning electron microscope. What I'm showing here are some of the concerns of those mid-20th century metallurgists, ceramists, geologists, and biologists. You would prepare samples that would be potted in a material, a resin, and you would polish them with various grits, abrasion, bring them down to a mirror smooth finish, probably with a final diamond, and beyond that maybe a aluminum oxide polishing step, and then do some etching. And then hopefully you can see my marker here. You would look at the grain size and for things like twins and if there are particles in the grain boundaries and so on. But you were looking through a microscope and you really had no way of going in and doing a chemical analysis. Also, you may have an interest in bonding materials together. For example, plating one material on another and then seeing as a function of temperature how those materials might diffuse together and study interdiffusion. And what you were challenged to do was to find some way of being able to do a chemical analysis on this really fine scale. I'm going to take an even further look back without getting into hardly any detail of some of the early days of science, because everything listed on the left side of this slide is a discovery that somehow is relevant to the topic at hand today. And if you draw your attention over here to the right-hand side of the image, you'll see that way back in the middle of the 19th century, latter part of it, people were they had developed some fairly primitive vacuum systems. They were developing some battery technology. And so what they would do is they were studying electrical conductivity. They would take a glass tube and bring it down to not super low pressure, but a low pressure, and then put a voltage supply across it. And they would see a stream of something coming out, which would strike the surface of this glass plate. Here's a Maltese cross, and it would show a pattern of it. And it was in this way that J.J. Thomson discovered the electron, because he found that this was not electromagnetic radiation that was being generated, but it was particulate. The name electron would be named at another time by a fellow named Stoney. But if you put a magnetic field there, electrostatic field, you could deflect it. And it's kind of funny when you look at this device, because you see within it the embryonic form of the cathode ray tube, of the scanning electron microscope, of a whole bunch of stuff, of radar. And this is really kind of amazing how this relatively simple experiment led to so many important developments. As a matter of fact, when one of these tubes was covered up with some black paper, Röntgen, back in 1897, found out that a screen of something that he left on a workbench started to glow, and that was the discovery of X-rays. So this rather simple device, you can actually buy one of these tubes on the internet for about $30 or $40. I have one around here somewhere. I just need a power supply to a 5 kV power supply to fire it up. But it's a really relatively simple device. So let's go back even a step further, and believe me, I will take some into more modern technology in a moment. But way back in the early part of the 19th century, Fraunhofer had developed an instrument called the optical spectrometer, which made it possible to disperse light with a prism, for example, or with a grating of some type, coming from a source. And in his case, the source was the sun. And he could develop an image, which was a spectrum of various materials. And he noted in there that there were some absorption lines. And those absorption lines later were found to be attributable to different radiation from different elements being absorbed in the Earth's atmosphere. Just a little later than that, Kirchhoff and Bunsen, the same guy who developed the Bunsen burner, found that if you were to oxidize certain fuels, that you could also get a spectrum. And this spectrum would show various emission lines. And a scientist by the name of Rydberg found a very simple relationship. And I'm not going to show a lot of equations in this talk. Don't get too nervous. And that 1 over the wavelength is equal to a constant, which we call a Rydberg constant, times 1 over an integer n sub f, which was for final state, and 1 over n sub I, which was for the initial state. And these were just numbers. They had no physical meaning. And this, of course, was before the Bohr model was even developed. So there was something there. There was some unique relationship between the spectral lines and the elements that were there. So let's take a quick look, as I'm sure all of you have before, no pun intended, of the electromagnetic spectrum. And what we see is a visible spectrum that runs, I don't know, from about 400 to about 700 nanometers. Convert angstroms are, you've got 10 angstroms in a nanometer. And that's what we see with our eyes. If we look at shorter wavelengths, we get into ultraviolet, even shorter X-rays, beyond that, gamma rays and cosmic rays. And on the other end of that is infrared, microwave, radio frequency. And it turns out that each part of the spectrum can tell us something about materials. And so what people have done is to develop techniques that allow us to look at what elements are present in material, and in the case of molecules, what molecular details of molecular structure. Now, in those early days of the 20th century and the end of the 19th century, scientists encountered something called the ultraviolet catastrophe, which refers to the fact that if you looked at radiation from what was called a black body, just something that was heated up to a high temperature, that at very short wavelengths, in the ultraviolet, from existing theories, that things would explode. That was the catastrophe. There would just be an enormous amount of intensity. And along came Max Planck, who showed that, in fact, the energy is quantized, and that it's equal to the very simple formula there, h times nu, where h was a constant. And so energy was really in packets. The other equation on the right of it is really definitional. That is, its frequency equals C over lambda. And by definitional, I mean C is in centimeters per second. Lambda is, say, in centimeters or nanometers. We are going to do there, but if you cross out the length dimension, you have 1 over time, and that's frequency. Combine the two, you have E equals hc over lambda, and energy, if you put the numbers in there, is roughly 12.4 over lambda in angstroms if the energy is in keV. So a common example of that would be what we call a copper K alpha line, has a wavelength of 1.54, blah, blah, and an energy of about 804. So there was an experiment that was done by Rutherford in which he was looking at the scattering of alpha particles in thin metal foils. And what Rutherford found, much to everyone's surprise, is that there was a small but very realistic measurable amount of backscattered electrons, which was the same as they said then of firing a cannon at a piece of tissue paper. Nothing was going to bounce back. And the only way that this could be explained was to assume that the positive charge in a material was located in very small regions, which we refer now to as atomic nuclei. And this was a change over something proposed by J.J. Thomson, which was called a plum pudding model, in which it was thought that electrons were sort of floating in a sea of positive charge. But now this is leading us to the idea of atoms and what we call the planetary model, which is well over 100 years ago. Man, when I was in high school, people even sort of taught that. This is before quantum mechanics, and at least the quantum mechanics of today. So that model is obsolete, incorrect, but it's quite understandable. It's nice to think of the solar system model with electrons going around in various orbits. And this model from Bohr led to a very simple formula here, which was the energy of a given level was equal to a constant 13.6 times the atomic number squared over n squared, where n is something which we call the principal quantum number here, principal number, which refers to which row you're in. So this is n equals 1 is the first ring, n equals 2 is the second, third, and so on. At that time, people weren't aware of the existence of neutrons. They didn't really show up until Chadwick discovered them in 1932. Now, again, in that incredible laboratory in England, there was a fellow by the name of Henry Moseley, who in 1913 was studying spectra. No real theoretical model here, but we see a picture of Moseley, who sadly died in the trenches in Gallipoli in World War I, holding one of those tubes like I just talked about. And if you collected X-ray spectra, as shown in the lower right, you could see that each X-ray, each element provided a unique set of spectral lines. And what was also interesting, if you look at the very bottom one, which is brass, that you see the same lines as copper. We don't have a picture of zinc here, but that the lines are separate. That is, an alloy doesn't show the line shifted. It shows a distinct spectra. And Moseley sort of put this together in the equation you see up there, which was based on his observations, in which there was this unique relationship between frequency and atomic number. And you can also get a hint of that looking back at Bohr's equation from an earlier slide, but this plot shows atomic number versus wavelength if you choose on that scale on the top, or square root of frequency on the bottom. And this is the missing link. This is how you can identify elements based on their X-ray spectra. Now, later on, and as I said here, don't worry, I don't want you to memorize or think too much about Schrodinger's equation. This is actually a non-relativistic equation. Later on, Dirac would come along and make it fancier. But electrons were described as something called psi, which was a wave function. Here's the central potential associated with the nucleus. You know, messy stuff for sure here. But, and then Born, not Jason Bourne, but Max Born, showed that if you squared that, it had to do with the probability of finding an electron in a given place. And so then the atom, the picture of the atom became a lot fuzzier, with the planetary orbits being replaced by these orbital things, which you'll learn about in some of your more advanced chemistry classes. But now the energy levels, as shown here in the picture on the right, are now described not by one number n, but by a group of numbers, n being the principal quantum number, as was the case for Bohr, but also some fine structure associated with angular momentum and magnetization and spin. And so when we look at that picture on the right, we see a nomenclature there, K, L, M, N, referring to first, second, third, fourth levels. So the numbers that we see over here, N is the principal quantum number, 1, 2, 3, and so on. And so we see this fine structure. And then the second number, S or P or D or F, refers to the angular momentum, and other numbers start referring to the spin. And now we can start getting into understanding the terminology associated with spectra. If we have a transition from the L3 level to the K level, that's called the K alpha. And from the L2 level to the first level, that's called the K alpha. Sorry, that's K alpha 1. This is K alpha 2. And you'll notice there's no transition from the first level in L to here because there's some rules of the game. And the second number, S, angular momentum, is a quantity that must be preserved. And when a photon goes off, it has an angular momentum of 1. So this delta S would be 0 in this case, so that would be forbidden. And there are people who can calculate not only the probabilities of transitions, but also their relative intensities. Frankly, I don't know how to do that, but it has been done. But a point I want to make here is that we see that this X-ray spectra is relatively, can be relatively simple, and that we have a K alpha and a K beta. There's actually shown here as 4 K beta lines, but they're going to be tended to be kind of grouped together because they're not that far apart in energy. And so that gives us K alpha and K beta. And then we can have L series, which refers to transitions into the L level, and M series and so on. And they get a lot more complicated. And if you have any experience with optical emission spectroscopy, you're talking about energy levels that are much further out, and they're just really nasty, complicated. So here's our Bohr atom again for purposes of illustration on the right-hand side. And we see our incident electron from our electron beam coming in, and it ionizes, that is, it knocks out an electron, in this case in the K shell. And that caused the ejection of an orbital electron and a scattering of the primary electron, which will have lost an energy equal to the bonding energy. This is the basis of people call EELS, electron energy loss spectroscopy. And then an orbital electron gets flipped out somewhere. That may wind up as a fast secondary. Now the atom is then left with a vacancy, as we see here in the middle picture. An electron from a higher level drops down, fills that vacancy, and then one of two things happens. Either an X-ray is emitted, as shown here on the right, and that's X-ray emission, or the energy is converted to another electron, and that electron is called an Auger electron. And there are Auger electron spectrometers as there are X-ray spectrometers. If we look at the picture on the left, it relates the amount of energy required to ionize an atom to the atomic number of that element. And that could be called excitation potential, ionization energy, or critical excitation energy. But what you can see is, let's talk about copper, 29. We're going to need about 9 kilovolts to excite it. And after that, if we try to excite something in the middle range of the atomic number, we're talking getting 20 or 30 kV out. And with most SEMs, we're not going to be running much over 25 kV. And furthermore, if you look at this rather crude equation down here, it says that the intensity of the line is proportional to the ratio of the beam energy divided by this excitation energy minus 1 raised to some power. 1.6, 1.7 is only an approximation. So if our critical excitation energy is the same as the beam energy, this is 1 minus 1 is 0. There's no intensity. And by the way, this is the intensity that's generated within the sample. The X-rays still have to get out, and if they're you may be losing some of those on the way out. We'll get back and talk about that point later. Now, I mentioned before that you can either get X-rays out or Auger electrons. This is a plot of what's called a fluorescence or fluorescent yield as a function of atomic number, particularly for K-level ionizations. And the point to note here is that for a very low atomic number, that only a very small fraction of the ionizations actually lead to the emission of X-rays. The fluorescent yield is very small, so most of the energy would go to the emission of Auger electrons. Now, I could show you plots for L lines and M lines, but take my word for it, to look like a shotgun was fired at the graph. They're very complicated. But before I leave this slide, let me mention that not every electron leads to an ionization. When we talk about the regular operation of a scanning microscope, we know that the backscatter fraction could be as high as, say, 50% if we're bouncing electrons off of gold. Not much of a function of the beam voltage, it's high. Secondary electrons are less, but our detectors are more efficient, and we can get a lot of signal. But here, when we're talking about the production of X-rays, we're talking about maybe only 1 in 1,000 or 1 in 10,000 of those electrons will cause ionization. And the name of the game, as we move forward, is to get as much signal out as possible. So X-rays are nowhere near as efficient as electron excitation. Now, to perform chemical analysis, we've got to simulate X-ray emission and measure the X-ray wavelength for that. By the way, we could have done that with protons, or we could have done with X-ray, that's XRF, but here we're talking about electron excitation. And then once we get the emission, then we measure the intensity of spectral lines, and we can convert that to chemical composition. Now, Castaigne, in his dissertation, published in 1951, did almost all of that. But this was refined by a lot of people, and I just tossed a bunch of names out here, and I probably missed a lot of people. I noticed I didn't put Bill Bastine's name down, who had done a lot of work on Phi Rho Z. But he sort of did the groundwork for this in his dissertation and in some papers that followed later. But his method of looking at X-rays was to use a crystal diffraction spectrometer and the microprobe. So you see here on the right-hand side is an early version of that in which you use an optical microscope coaxial with your electron optics to look at the sample, see where you were, and X-rays would come out, bounce off a crystal, and go to proportional counter. So if we come over here to the schematic, we have electron beam, ionizes a sample, X-rays go off in all directions. Some of them will come to the crystal spectrometer over here, which is basically a relatively low collection efficiency, and bounce off if Bragg's law is obeyed. And Bragg's law, you hopefully recall, is something that states n lambda equals 2d sine theta, where n is an integer, let's say it's 1. Lambda is the wavelength, d is the interplanar spacing of a crystal, and theta is the angle of incidence. And what you do is you scan theta and you collect any X-rays that are reflected. And then you have to go into all this electronics over here. But basically, your results show up as a plot of intensity versus Bragg angle, or in most spectrometers, they're called linear spectrometers, it's intensity versus the position of the analyzing crystal, which is moved linearly outward. And the crystal, you'll notice here, is bent. It has to be curved to meet what are called focusing circle requirements so that you get the same angle of theta across the face of the crystal. And this was really the basis for microprobe analysis, from the early days and still today. If you look at a spectrum done with a microprobe, this is just a iron, chrome, nickel, vanadium. I don't remember all the stuff that's in this alloy. You see that you got pretty good dispersion between various elements. However, with a microprobe, you needed different crystals to look at different wavelengths, because if you think about Bragg's law, say lambda equals 2d sine theta, say that theta can never be greater than 1. I'm sorry, sine theta can never be greater than 1. So lambda can never be greater than 2d. So if I use a lithium fluoride crystal that has a day spacing of 2 angstroms, I'm limited to wavelengths up to 4 angstroms. If I want to look at longer wavelengths, which are associated with lighter elements, and they are because the electrons are not as tightly bonded to the nucleus, then I need a larger crystal. I can only get up to about 10 angstroms with a natural crystal. So people started developing using lead stearate, multi-layers, and eventually use semiconductor techniques to build what they call layered synthetic microstructures, which allowed you to look at fairly long wavelengths. Here's some work I did a long time ago, looking at the difference between boron, cubic boron nitride, and hexagonal boron nitride. And this is a fairly long wavelength, which means these are quite low energy. And what you can see over here is, let me see if I can, okay. What you see over here is that you see a peak shift slightly and some additional peaks. Once you get into, you have to distinguish somewhat between core shell ionizations and ones which are out at higher levels where various orbitals start getting shared between different atoms. And for these light elements, you don't have a lot of electrons there. And so in a material like boron nitride, the fact you get these extra peaks have to do with some electrons from nitrogen can come over and say, hi, boron, and wind up there. So we can get very fine structures, which are visible with diffraction-based spectrometers, but much so less with energy dispersive spectrometers. Now, let's go back now, instead of a tale of 2 cities, to a tale of 2 rooms. And I'm not sure about this date. It could be 68 or 69. And here was the story. When I was at GE, I had a room that had an old Cambridge stereo scan, or a new one, I should say, at the time. In one place, this was behind curtains, had to be dark because you had to photograph the display. And on the other curtain was the microprobe. As I mentioned before, a lot of companies, you were either a microprobe person or an SEM person. You wouldn't necessarily talk to each other. And then in 1966, there was a paper in Science by Bowen, which showed that solid-state X-ray detectors could be used for X-ray analysis, that they had some reasonable energy resolution. And so the 66 paper talked about use with X-ray fluorescence. And then in 1968, there was a paper published by Ray Fitzgerald, Klaus Keil, and Kurt Heinrich, in which they put a detector with about 500 plus EV resolution, so it's pretty low resolution, not very good resolution, on a microprobe, which showed you could do it on a microprobe. So one day a salesman walked in through the door, and he brought with him a radioactive source, a penny, and an X-ray detector, and he set it up on my sample preparation table. And he shined the radioactive source on the copper penny, picked up the X-rays with the detector, and showed me the spectrum of copper. And he said, well, people are starting to do this on microprobe. Would you like one? I said, sure. And I got one. I said, by the way, let's go behind curtain number 1. And there was my scanning microscope, Cambridge stereo scan. At that time, nobody had ever put an X-ray detector, solid-state detector on a Cambridge stereo scan, which was the most popular microscope at the time. I was to learn later that John Ross had in fact done this with the JULU2 at JUL in Peabody, I think is where they are in Massachusetts. But this was the first time ever on a Cambridge. And so I'll show you in a moment some results, but I reported that in the Cambridge Stereo Scan Colloquium in 1970, which was sort of a precursor meeting before the Johari SEM. Well, let's show you quickly how this thing works. We have a semiconductor, which is intrinsic. That is, it's not a p-type or n-type. It has no extra energy levels in here, and we have a filled valence band and an empty conduction band. An X-ray photon enters, and of course its interaction will be, X-rays don't slow down. They have a photoelectric interaction, and they'll liberate a high-speed electron, and that electron can produce electron hole pairs, as shown over here on the right side. So we have a certain number, n, of electron hole pairs, and that number is equal to the energy of the X-ray divided by about 3.8 eV. For silicon, it's larger than the band gap, but silicon's an indirect band gap semiconductor. But you can see, for example, if my energy is 8 kilovolts, which would be copper, and we say this is roughly 4 eV, then we would produce about 2,000 electron hole pairs. Very small charge, but detectable. So over here, in comes our X-ray, produces the photoelectron. We put a negative potential in the face of this thing, and so positive holes will go this way, and the electrons will go over here to the gate of a field effect transistor, and we're off and running. So here's the early, these were called lithium drifted silicon detectors. They required liquid nitrogen to cool things down because there was a lot of thermal noise that would obscure any signal. And then what we have here is our electron beam striking the sample, producing an X-ray. The X-ray enters the silicon detector, produces electron hole pairs, goes to the FET, which is part of a charge-sensitive amplifier. There's a conversion of charge to voltage. And then our spectrum now is a plot of intensity versus energy. And what we have here is something called a multi-channel analyzer, which is like computer memory, which is divided into different cells. Each one corresponds to a certain band of energy. So this technology was definitely a game changer, but there were issues. The resolution needed to be improved somewhat. Count rate limitations were problems because of pulse pileup, and detectable elements were limited due to the windows they originally had on the early detectors, and these things had to be cooled. So what did the first spectra look like for me? I've got a picture from the proceedings of the colloquium. Sorry, you can't see them very well, but if you look at the upper right, you can start to see some dots over here, and this would be like 10 eV per channel. And so I might have 500, 1,000 channels. At 10 eV per channel, I could cover 10 kilovolts. And this was a fracture sample, I think, of a steel, and there were some particles here. So this is cool. You could get a nice qualitative analysis of it. When I look back, I think about how funny some of this is. I had to count those dots, somewhere between and pray that the phone didn't ring or somebody interrupt me and I lost count. And a great technological innovation was when someone came up with the idea of intensifying every 10th dot. So you could get up to the peak and do them 10 at a time. The vertical deflection there refers to the intensity. So let's look at the features of an EDS spectrum. It's a plot of intensity versus energy, and the characteristic lines we talk about are due to the coarse ionizations I've discussed. But we also see a broad background through here, which is called the continuum or Bremsstrahlung, which in German means braking radiation. And it's due to the fact that as an electron accelerates, changes velocity, thanks to Mr. Maxwell, we're going to get the emission of electromagnetic radiation. Like I take an electron, I spin around in a synchrotron, I can get radiation coming because this acceleration vector is changing. So it's this broad background, which is the problem, because if it's too big, we may have trouble seeing some of these peaks. Now in X-ray spectroscopy, I'll go way out here. You notice the continuum drops down at 35 kV. I can tell this was done in a microprobe that was being run at 35 kV. That point there is called the Duane Hunt or short wavelength cutoff. So you can actually tell what your beam voltage is by seeing where the continuum drops off. In cases where you have charging samples, you will actually see that even though your instrument says I'm running it at 20 kV, it might really, this cutoff might be at 15 kV because your sample is charging. And then you can get artifacts which are associated with are called escape peaks and sum peaks. And the sum peak I'll just mention is when two X-rays enter the detector at the same time with the same energy, but can't distinguish between them. So let's go back and look at our detector basic operation again for a moment. The number of electron hole pairs is equal to the energy of the X-ray divided by this 3.8 eV per hole pair. If I multiply that by the charge of an electron, that tells me the total charge. If I take that charge and put it on a capacitor, I now have voltage, and I can increase that with a gain. And the bottom line here is that the voltage is directly proportional to the energy. And there's a constant in here. And I can change that constant by changing the gain of the amplifier. So when you're aligning one of these things, calibrating it, you might put in two different elements or take copper K and copper L and do a little bit of adjusting of the gain and maybe an offset to get your system calibrated. So what's coming out of the device is a pulse of charge. It goes to the gate of an FET, winds up on this capacitor. So this is a charge to voltage converter. And so we have a step over here. And the height of that step is an indicator of how large the X-ray energy is for each pulse. And in older systems, these would go to pulse shaping amplifiers. But nowadays we can just go right in there and look at that. And so this brings me to sort of the next level of what was happening. And that is that the silicon, not the lithium drifted one, what we call the SILI detector, but silicon drift detectors were developed in the 1980s, which had a different structure. The X-ray still entered through here, but the anodes, you had all these voltage rings, and you had this central anode, which resulted in a very low capacitance. Plus, this thing could sit on a Peltier cooler, which you get down about minus 20 C, and therefore you didn't need to keep on refilling it with liquid nitrogen, which was great. And then all the electronics was switching over to digital electronics and better windows like silicon nitride or even some windowless modes were done. So we're talking about getting higher count rates. And then the question is, well, what about a higher energy? Well, this just shows the step function that you see and how good your signal to noise is, because the signal is noisy and you want to kind of average it out. depends on how long you sample it for. But if you sample it for a long time, then you're more likely to get in a pulse pileup situation. So without beating this thing to death, the blue, I just took this out of the literature, is for a lithium drifted silicon, the old style. And here is the new silicon detectors, the drift detectors. And what they basically show is that at 5.9 kV, which is either iron or manganese, I forget, you're talking about 100 eV. Let me say something more about resolution. Say a few things more about resolution. The natural line width of an X-ray line, as determined by the other manifestation of the Heisenberg uncertainty principle, the delta E delta T part, being greater than H bar, is about 1 eV. So these lines are inherently very sharp. With a good crystal diffraction spectrometer, you get down to about 10 eV. With an EDS, the full width at half max of those peaks, it kind of goes as the square root of a noise term squared plus a constant, which we'll call a Fano term, plus the energy. So the energy resolution is a function of the energy of the line. But without going into details on this graph, basically, there is a limit. When noise is 0 and you're looking at iron, you have a limit of about 100 eV. So why do we care about resolution? Well, we want to avoid peak overlap. Here's an EDS spectrum taken of a 304 stainless steel on the left. If you notice over here, we have manganese, K alpha and chrome K beta. Well, they're only about 52 electron volts apart. So if I have a detector, even one that had 140 EV resolution or 130 or maybe state of the art, even a little less than that, they're going to appear. You remember manganese, the manganese is about 1.8%, chrome is about 18%. They're going to appear very close. Those vertical lines show you where they are. And yet over here, if I look at the same thing with a wavelength spectrometer, which has 10 times the energy resolution, not only can I split the chromium K beta from the manganese, I'm even splitting out the manganese K alpha to K alpha 1 from the K alpha 2. Now, we also are interested in detection limits. And I think it's important to bear in mind basic counting statistics. The standard deviation of that is of a count goes as the square of the counts. So let's say I have 100 counts that I measure at a peak. 10 is the standard deviation. I want a signal that I measure. I'd like to have it 2 or 3 times greater than that to know it's real. Otherwise, if I keep on repeating the measurements, comparing a peak to its adjacent background, I might be very disappointed and see that, oh, I saw something there now, but next time I see it, now I don't see it, it's not there. So imagine the following experiment. Let's say we have a sample or electron beam and 2 detectors. One has really great resolution, could be a diffraction spectrometer, or the best state-of-the-art EDS. The other one is not so good detector. And so what we see here is peak 1 from the high resolution spectrometer is only sitting over a very small amount of background, because assume the continuum is fairly uniform over this range. And then peak 2, where the resolution isn't so good, is over a larger background. So even though both of these detectors have the same efficiency and solid angle, so peak 1 equals peak 2, the backgrounds are different, and therefore the peak to background ratio is going to be worse for a low resolution detector. I just talked in some numbers here. So let's say I had 10 to 1 peak to background ratio and 10,000 counts per second, 10 seconds. From the old Z-Bold equation, I would come up with roughly 3,000 parts per million. That's 0.3% for a detection limit. Can I do better than that nowadays? Yeah, maybe a 0.1%, maybe even 500 ppm. That's pushing it. The best I ever did with a diffraction spectrometer was iron and aluminum. And I remember doing that at at 50 parts per million. So there's still a way to go to get to these lowered limits. You're not going to look at boron and silicon at a part per million. And so there is, there definitely are limitations. Now, what about peak intensity itself? I mentioned that before that we have this simple equation for generation. But when you look at the chain, the important thing in that constant K is to recognize that your signal always varies directly with probe current. So one of the reasons why this thing really didn't take off right away with scanning microscopes, because we're talking their currents, particularly in the early days, even with lanthanum hexaboride, we're talking about currents that might only have been, in the neighborhood of 100 picoamps or something when you're looking at a really small spot. The microprobes were typically running at currents that would even run up to a tenth or even 1 microamp. And I usually had 2 lenses rather than 3 in those early ones. And so, current was a big issue. If you don't have a lot of current, you don't have a lot of signal, your peak to background ratio goes away, not only for your X-rays, but even for your SEM images. So if you'd like to increase the current, that's good. We got some great Schottky and FEG sources now. But you're also limited, as I said, by the fraction of ions that you materially ionize that leads to X-ray emission. Your soliding of your detector is important. The efficiency of the detector is important. So all of these things can affect your response. If you want to improve detection limits, then you may want to go to a large detector, but that may decrease your resolution. For light elements, that's great. We can go to thin windows, we've got silicon nitride, but they could be fragile and there's moisture issues. Way back when environmental SEMs first came out, I tested the first one out, the old electroscan, and I was looking at water with metals dissolved in it, and that was great up until the time that the water vapor penetrated the thin window on there, and I had ice buildup on my detector, and then the whole thing had to be heated to get the ice off of there. I mean, to make this point a little clearer on this relationship between probe size and probe diameter, you can derive a relatively simple equation for a thermionic source that says that the probe current varies as the diameter to the 8/3 power. Make that a cube. And what you're saying is every time you have the size of the probe, you're decreasing the current by an order of magnitude. Okay, how about peak to background ratio? Well, I could improve that by going to higher voltage, but I might run into absorption issues. I could also count longer, but then it's taken more time, but I might improve the contamination. And also, okay, and what if I'm taking a map compared to a point analysis? You can take some pretty beautiful maps. Again, I'm stealing from the literature, and map out different elements with EDS, even with fairly high spatial resolution, as shown on the right. But some of those new detectors have pretty high count rates, well over a few 100,000 counts per second. But think about it. If I do 1,000 by 1,000 image, I'm only dwelling on any given point. If it's a 1 second count, I'm only sitting on that point for a microsecond. Okay, I'm trying to keep an eye on this time. I got a few more comments and we'll finish up. Quantitative analysis, you need a sample and a standard. You make a ratio of sample to standard, and then you convert from this K ratio to composition. This can, for a binary system, is easy to visualize this. People used to actually make up the standards and make calibration curves of K ratio versus composition. Tom Zebold, one of Rob Ogilvy's students, years ago came up with a relatively simple equation between the K ratio and the C, but you needed to determine what this A parameter was. And you could do that just with a single analysis. I just wanted to bring up another point, which is kind of a subtle point, and that is when you push that button and do quantitative analysis, of course, all this now is all turnkey. the question is, why does the composition show up usually as weight fraction? So what's shown here looks like a very messy equation. Just remember equations, if you got the terms, you plug them in. And this is a calculation for how much X-ray intensity you should get for a given sample of a given composition. And what happens is you have to take into consideration the fractional solid angle of the detector, the number of electrons striking it, striking the sample, the collection time, and all the stuff on the right, which is a way of computing the actual composition of the material from relatively simple base principles. The trick here is that in here is density, grams per cubic centimeter. And so you have to use weight fraction for C to get the grams per cubic centimeter of the element of interest. Earlier on, I mentioned, and you look at this equation, you'll see also this thing called Q. Q is something called the ionization cross-section. And this just shows a plot of Q versus energy for a whole bunch of different processes. Way up at the top of this is copper, function of voltage. Way up at the top is elastic, so that'd be like backscattered electrons. So this is the cross-section per atom. It's a real small number, but if you calculate the number of atoms in the region you're looking at, it could make it quite high. The main point I want to make is here's K-shell ionization. It's about 5 orders of magnitude less. So even though you can produce lots of backscatter electrons, lots of secondary electrons, you may be not getting a lot of X-rays. The relationship between K and C, don't have the time to talk about this, is done for you automatically. And I just want to make a couple of additional comments and we're almost done. It's very important when you look at a spectrum not to assume that the line with the most intense peak is in fact the one that's present most. When the high temperature superconductor came out, YB2, YBA2, yttrium, copper, barium, YBCO 6.8, I think it was. Y1, B2, BA2, E3, can't remember the exact numbers. Oxygen 6.8. If you took a spectrum of it at 10 keV, oxygen was the highest peak. Barium was the smallest. And yet this is at 10 keV. If you go to 20 keV, all of a sudden these things reverse, including the relative intensities of the copper L line and the copper K line. And why is this true? I already mentioned the fluorescent yield can be quite different between elements. You can also have absorption effects. KV can affect things, and the tilt can affect it. So if you take no other message, don't take an analysis, don't do analysis in front of somebody where you say, oh, look, there's the biggest peak in the spectrum. There must be more of it. That's not how you play the game. You got to be very careful and relate it to a standard. I'll mention, and again, I'm over a couple of minutes, and I'm almost done. Spectral artifacts. When you hit your sample, it's possible, as shown here on the left, that the electrons can scatter all over the place and give you signals like from the pole piece, which is iron, which isn't in your sample. But perhaps the more dangerous thing to worry about is beam penetration. Here's tantalum carbide inclusion, nickel chromium. Grab some water. Could only have a minute left. The tantalum carbide particle contains at low voltage the beam. That's where the X-rays are. But if I go to higher voltage, then I'm going to get everything from the nickel chromium alloy underneath. Excuse me. Finally, the last subject I think I'll mention is spatial resolution.
we can get down to really small probes, but realize that these are Monte Carlo calculations, that you can cover a very large volume of material with scattered electrons. And you really have to go to thin films, which is shown on the right. You get, this is a nickel aluminum film, to get the highest spatial resolution. Here's 10 nanometers with a 50 nanometer film. It hasn't expanded much. Over here in a bulk sample, you got stuff coming from all over the place. So, added comments in the future. There's some great software out there. I highly recommend, if you can get it, get a hold of TTSA 2. TTSA 1 was written by Fiore. But this one by Nicholas Ritchie is terrific. And that's a NIST, and you can find it online, and also Casino 2 to do Monte Carlo calculations. There's lots of useful books. I think energy resolution for EDS is near the limit. People have talked about some other techniques like a microcalorimetry, but the spatial resolution is in fact getting better. People are also getting much better at 3D mapping, slicing thin samples and doing 3D maps. And I see a lot more correlative microscopy, if you want to call it, with things like EBSD and with the Raman spectroscopy. And then I see some improvements coming along in spectral deconvolution. So I'm over a tiny bit, but not too much. So thank you very much for your attention. I hope you found it useful. And at this point, I'm going to turn it back over to Jeff.
All right. Thank you, Eric. Appreciate that. We have a few questions, okay? Tony Bragg, how does dead time affect signal to noise ratio? Do you want more than 30%, less than 30%, but more than 0?
Thanks. You want, you'd like to have typically less than 30%. Dead time is not your friend. Obviously, you got to, particularly you're comparing a sample and a standard, you have to compare them with equal lifetimes. You get a meaningful ratio if you're doing analysis relative to standards. But I would try to keep it below 30%, because if you start getting up really high, you're going to get into a lot of peak pileup issues, and things will just start getting messy. You don't have to bring it to 0 though. And so okay. I think 30% rule isn't too bad.
Okay. Another question from him. What about working distances? How does that affect EDS accuracy?
I don't know how it will affect accuracy. In general, as you change the working distance, you're also changing what's called the takeoff angle. That is the angle at which the X-rays emerge from the sample. And so if you make an error in a takeoff angle, you're going to produce errors in your quantitation. And I wanted to say one thing, which again, I could do a whole lecture on, is absorption, particularly as you get down to light elements. The absorption factors are not really extremely well known. And you can get into significant errors in the absorption correction, which will make your results a lot less accurate. Whether there's a preferred working distance, I don't know. Probably you just want to know it exactly to get the proper takeoff angle. You do need to know that takeoff angle as accurate as possible.
Okay, great. All right, thank you. Okay, so Annette has a question, Vanderhunt. Are there particular challenges from an EDS detector perspective from radiation in the analysis of nuclear materials by EDS?
I think there probably are. I remember in the early days of microprobes that a lot of places who had nuclear facilities had to have specially shielded electron probes made for them. But depending on the energies of the radiation, if you're looking at radioactive samples, if those energies are X-rays in that same range, it's going to be a problem.
Mhm.
Alpha particles probably would bounce, would probably not penetrate. Electrons, I'm not sure would be a problem. I know that some detectors have magnets in front of them to get rid of scattered electrons from entering. So maybe it would affect the beta part. Depends how much energy it has. Depends what the energy is of those radioactive components. I've had no personal experience with any of that.
Okay. All right. All right. I have another question here from our friend Farber Kug. Can you do EDS while imaging under cryo-SEM conditions? Huh.
I'm
Good
saying because I've never done anything under cryo SEM conditions.
Right.
Jeff, you may have some ideas there. What's the vapor pressure associated with those cryo devices? Because if you have a lot of vapor
well,
pressure,
you're going to be at negative 180 C or somewhere in that area. You know,
so I would worry about anything that would give you moisture that would get to your detector, but that sounds like not highly likely if things are cold. So my guess is it's probably okay, but again, I have no experience in that at all. Just like the
yeah.
radioactive.
So definitely, there's definitely been work out there done in a lot of different ways, okay, with battery materials and cryo. So I think, yeah, so you can definitely map. You could do, there's even situations where you can, we actually have a Peltier stage, that we offer that that goes to negative 100 C for, battery materials, and you can do EBSD patterns with that. You can mill. Yeah, so I think it's definitely possible, and I think it's all about the configuration and and how you're working with the sample, and then I think also it's important to know that the EDS design is going to be conducive to that, right? I think that's important.
Yeah.
So yeah, that's a good question. Very good question. What is the state? This is from Benjamin Ward. What is the state of uncertainty quantification for EDS? Are there commonly identifiability issues in EDS data? So, what is the state of uncertainty quantification for EDS? Question mark. Second question is: are there commonly identifiable issues in EDS data?
Yeah, I'll try to answer that one from a couple different angles.
Sure.
From what I've seen with any X-ray analysis, from a precision standpoint, it's usually around a couple of plus or minus a couple percent. Under conditions where you have elements that are present above, let's say 10%, you should also, on an accuracy point of view, be able to get within plus or minus 2%. I mean, a lot of people have tried to measure these things. So there's nothing better than if you come up with ways to cross-check your results. Let me just tell you about a quick story where I was interested in the accuracy of quantitative EDS years ago compared to wavelength diffraction spectrometers. And so the wavelength spectrometer, I analyzed the material that I had analyzed by conventional chemical analysis. So that gives you an extra decimal point or two on the quality of the results. And I then analyzed it with EDS at 3 different voltages. And every one of those values was different. and none of them agreed with the WDS that agreed closely with the chemical analysis. I mean, I think you got to be careful in terms of assuming that you've got really accurate quantitative analysis for a lot of reasons, like I mentioned with the absorption coefficients or the takeoff angle, or making sure you've got the right voltage or the right correction procedures. You know, if you can do 2% on some of the major elements, that's great. As you get down to things that are only a few percent or less, don't expect to get data which is better than about 5%.
Okay, great. Okay, good. Okay. One more question. From your experience, what are the major sources of error in EDS analysis?
Well, I've mentioned a few of them, but this thing about looking at a sample and having the beam penetrate through the sample and cause the material around it to fluoresce, and thinking that those elements that you see are in the area that you're analyzing. What I'm saying is that the resolution for chemical analysis is usually much worse than the SEM spatial analysis resolution. And so you can get yourself into trouble. And I remember years ago reviewing a paper, it may have been for Science, in which somebody claimed that there was some metal in a particular sample, which I didn't believe was there. And I tried to reproduce that. And I found that what was happening was the area that I was looking at was fluorescing, causing some fluorescence of one of the elements to travel some distance away and excite elements from surrounding area. Another example of that is, let's say, and this is an experiment that I did. I took a copper grid and I had a fine carbon film on it, and I dispersed some tantalum particles on it that were few, tens of microns in size. Particles that were way away from the copper grid. So if you look straight down at it, you wouldn't see anything nearby. And yet, when I collected the X-ray signal, I saw copper. And what had happened was the electrons were scattered by the tantalum particles and were redirected and hit the copper, even though it was microns away. So I think you have to be super careful about thinking of experiments where maybe you change the voltage or you change the lines that you look at, just to be sure that you're not somehow fooling yourself.
Okay, great. Nice. All right, that was it. I think that's it for the questions. Great questions. Eric, great job. Thank you. We really appreciate your.
Thanks everybody for taking the time to.
Yeah, it's been great. I think this was really valuable, and to the participants here, if you have any feedback from us on any other seminars or webinars you'd like us to do to go into an area, whether it's with EDS analysis or something else that you're involved in, feel free to give us some suggestions. We're open to expanding our educational component here at Rave Scientific. Wanted to thank everybody today for participating. Have a great day, and look forward to seeing you all out in the field. Okay, have a nice day. Bye-bye.
All right. Thanks, everybody.
Bye.
Bye.
Hey, Eric.